are doing some form of performance tuning, and for DBAs who are fixing their developers' code. I hope the developers here are capable of fixing their own code. We'll see. Sorry, I think this is messed up a bit. That's better. Okay, so before we get started, that's right. I should fix that. Microphones and hairbands don't work very well together. So before we get started, just the remainder of the agenda for the day. I would note that if we run late, you guys miss the raffle. Or you guys ran out on me. I don't know which one will happen. I don't know what Neil's got planned for the evening session, so we'll see what happens when that arrives. But just as a reminder, if you have entered the raffle and you do want to win, you do need to be there. They're not going to send prizes in absentia. And the usual thank you to all of our sponsors, etc., so forth and so on. I'm going to spend most of the session looking at index architecture. Because once you understand how an index looks and how SQL uses the indexes, you'll be able to tune queries to use the indexes. You'll be able to design indexes to support almost any query that exists. Because the architecture is key to designing useful indexes. And I should mention that I'm talking almost exclusively about B-trees in this session. I might mention column stores, I might mention in-memory hackathon indexes, but these are, the majority of what I'm going to be looking at are the B-tree indexes, the traditional, old, on-disk row store indexes. Once we've looked at the index architecture, we're going to see how those are used for seeks and scans. I haven't actually got a slide on lookups specifically, but we'll talk about lookups when we get to that point. And then once we've got all of that, we can actually look at how you design indexes. So let's start with index architecture. B-tree. It's a balanced tree. If you've run across blog posts that describe SQL indexes as binary trees, please ignore anything those blog posts have to say. Yes, I have run into a few of them. I found one blog post that was quite fascinating, described SQL's indexes as a binary tree, drew an example index, and then proceeded for 3 pages to explain how SQL used the indexes, completely discussing it as a binary tree. SQL's indexes are not binary trees. Binary trees are way too expensive for indexing. It was quite amusing. The guy had basically fashioned absolute falsehood and then proceeded to logically explain SQL's behavior based on something that didn't happen. He should go into fiction writing. He was pretty good. So that is roughly what an index looks like. Hypothetically, of course, we don't exactly go and look in the data file. You don't see that on disk. This is what we call the root page of the index. Every index has a root page if it has more than one level. If it's only got one level, it is the root page. There's always one page alone in a level. Call this is a tree. It's an upside-down tree. The root's on top, the leaves are at the bottom. 0 or more intermediate levels. You may not always have an intermediate level. Small indexes will not have this level. And then at the leaf level of the index, this is for the clustered index, the actual data pages. For non-clustered indexes, the index pages for the index. With one exception, and only one exception, there is one row in the leaf level for every row in the table. I've also seen some quite amusing blog posts that describe SQL's indexing as storing one row for each distinct value. No. If we have a table that has 1 million rows in it, every index on that table will have 1 million rows at the leaf level. With one exception we'll talk about later. Doubly linked lists, so each page in each level knows its next page and its previous page, its parent and its child. These links work in both directions. So in the header for this page, you will find parent, next, and then in the details you'll find all of these links. Roughly. And by the way, this does not matter whether it's a clustered index or non-clustered. In fact, for quite a way, you won't be able to tell whether I'm talking about clustered or non-clustered indexes, because they look just about identical. Don't start, Hugo. All right, so a single column index. I'm not saying if this is clustered or non-clustered. I actually can't tell. It's impossible to tell. So we have so many rows at the leaf level. The intermediate page, the page above, contains one row for each page below it with the lowest value on that page. If that fits in a single page, that is the root. If that doesn't fit in a single page, as here, then we have another level above it, which has one row for each page below it. We keep building that up until all the rows fit into a single page. That is then the root. Happy enough with this? It's a fairly simple layout at the moment. If we have multiple columns in an index, pretty much the same things apply. These are two columns in the index key, and so the two columns in the index key persisted all the way up the tree, and we can tell what each page below starts with. Do note there is no way to tell what the page below us ends with. There is absolutely no way to tell from looking at this page whether this page contains E9 or not. We know this page does, but we don't know whether there's another E9 on this page. Now this is the first time I can tell you that this is a non-clustered index, because I've said it has include columns. But this could just as easily be a clustered index, a two-column clustered index in a three-column table. In fact, there's no way looking at this to tell whether this is a two-column clustered index on a three-column table or a two-column non-clustered index with an include column. No idea. Include columns are present only at the leaf level of the index. So our two key columns are still present in all the pages above, but our include column or our non-key columns in our clustered index, doesn't make any difference, are only present at the leaf level of the index. That's the main difference between an include column and a key column. And you'll note that the include columns also don't define the logical ordering. It's got absolutely no bearing on the ordering. It's just extra payload on the index leaf level. Everyone happy with this? There's a question, if anyone can tell me, not Hugo. How would I actually tell whether this is a clustered index or not? How could I tell, looking at this, if this is a clustered index on a three-column table or a non-clustered index, two key columns and include, without going to the index metadata, which will obviously tell me? Anyone? You're right, there isn't. What I haven't shown here is, there's very subtle differences, but for the majority of cases, you actually wouldn't be able to tell. I can tell you that I've obviously left out a uniquifier, because this is not unique. So if this was a clustered index, I would have another column here called the uniquifier. If this was a non-clustered index, well, then I'd need the clustered index key. But let's say the clustered index key was this. A non-clustered index would also have the uniquifier. I actually cannot tell by looking at this whether this is a clustered index, two-column clustered index on a three-column table, or a non-clustered index where the table's clustered on these two columns. Absolutely no way to tell, because these two indexes are quite similar in their internal structure. There's a few subtleties, but for the most part they behave the same way because they are structured almost identically. Right. So that's index architecture. Before we carry on, this is kind of important. Everybody happy with the index architecture, how the indexes are laid out? Right, a few points. This is logical ordering. This does not in any way mean that these pages are physically contiguous to each other. This page could be in file 1, that page could be in file 4 for all I care. This page could be the first page in the file, that page could be at the end of the file. It doesn't matter. These are indicating the logical order of the index. An index is not persisted in the file in physical order, unless it has zero fragmentation. Because fragmentation, by definition, is the difference between the logical ordering and the physical ordering. So if you've got an index that has 0% fragmentation, then it is laid out in the file physically contiguous. It doesn't necessarily mean the pages are going to be adjacent to each other. If you've got any fragmentation, all bets are off. That's why I get a little bit annoyed. There is still a TechNet article which claims that clustered indexes enforce the physical storage order. I know. It's annoying as hell. It's been there for enough years. Every now and again I make a comment on the forum saying, no, indexes do not enforce physical order, and someone posts this article as a correction. Dude, it's wrong. If you see an article claiming that either index enforces physical storage order, completely wrong. The futation is actually very trivial. Fragmentation is, as I said, the measure of how different the logical and physical orderings are. So if clustered indexes enforce physical storage order, then clustered indexes would by definition always have 0% fragmentation. Ever seen a 0% fragmented clustered index? Yes, no, maybe? I certainly haven't, except on a single page table. So, nope, unlikely. You should get something really low, but you're unlikely to get 0. Might be 2%. My favorite is the 5-page table, which has a fragmentation of 80%. So you rebuild it, and it has a fragmentation of 80%. I've actually seen fragmentation go up when you rebuild. The point there is the tables are really, really small. They're too small to actually be defragmented properly. So you take the table's got 40% fragmentation, rebuild it, now it's got 60. It's a 5-page table. That's just a difference of 1 page out of order. But no, and there's a whole bunch of reasons why a freshly rebuilt index won't be in physically contiguous order, probably most of which have to do with concurrent activity. But they might still be slightly out. You might get something down to 0. I doubt it. Sorry. All right. Fine. All right, so an index scan. If we are doing a scan of an index, there's 2 ways SQL will do it. Option 1, we do what's called an index order scan. This is probably the more common one. What SQL will do is it will start with the root page of the index. It's not looking for a value, it's just looking for the first page. So it will navigate down the index tree for trying to find the first logical page of the index, and it will read along the leaf level. That is an index order scan of an index. This is, as I said, the more common one you'll see. Do notice scan doesn't necessarily have to read the entire index. There's a bunch of conditions where it won't. For example, select min, this column from table, shows up as a scan, but it only reads 1 page. If we're going by the idea that there are 6 rows on each of these pages, then a select top 20 ordered by this will do a scan, 6, 12, 18, 4th page, done. We don't need to go any further, we've got what we need. It's still an index scan. Other way we can do an index scan is what's called an allocation order scan. And my diagram's actually slightly wrong here. with an allocation order scan, we're not looking at the root of the index. We're not navigating down the index tree. We're going to the index allocation map, the first index allocation map for the index, identifying the pages in the file that belong to this index, and then we're reading them in order that they are allocated in the file. So it's not technically this order. It might be this one, then this one, then this one, then this one, whatever. It's reading them literally in the order they are in the file. This one you won't see too often. There's two places I know of that you'll get index. So there's two places I know of that you'll get allocation order scans. That's a scan under read uncommitted and a scan when there's a table lock in place. Because this is susceptible to giving incorrect results due to pages moving around, page splits. When we've got a table lock in place, no other pages can move around, so we're safe. And under read uncommitted, that kind of inaccuracy is allowed. So it's and when reading a read-only file group. Because again, you can't exactly move pages around if the file group's read-only. I assume reading a read-only database will give the same behavior. So the two times we can get an allocation order scan is when the order of the pages cannot change, it's read-only for some reason, or we have a table lock in place, and that can be a shared table lock, by the way. It doesn't have to be an exclusive. Or we're under read uncommitted, isolation level, in which case the inaccuracies caused by moving pages around in the index are considered fine and valid. And by the way, they're documented as well. That's why no lock can return rows twice or three times and miss whole chunks of rows, because that kind of inaccuracy is allowed, documented to be allowed under read uncommitted. Anyone about to run away and take no lock out of some of their queries? I'm serious. Under no lock or read uncommitted, an allocation order scan can miss half a page of data here or there, or read it twice or three times. 3 times would be pretty nasty, but it's entirely possible. That's as the pages move around in the file. Right. Sorry. Personal sore pointers, no lock. Okay. So that's a scan. The point of it, the emphasis I want to make here for a scan is we're not looking for values. We're just reading the index. We don't know what we're looking for. We're either starting with the allocation map and reading, or we're just looking for a page, the starting page of an index and reading. I should mention that an index order scan can also go the other way, down to the last page of the index and read backwards. It's called a backward scan, perfectly valid. And you'd see a backward scan, for example, select max, column 1 from this table. You'd see a backward scan. An index seek. Implicit in an index seek is the idea that we are looking for a value. And the whole definition of an index seek is that we are evaluating a predicate against this table, or against this index. And in this case, we're looking for column 1 equals a particular value. So we can start, again, with the root page, and this time we are looking for a specific value. So we're looking for G. G is greater than A, G is less than K, therefore this way. Greater than A, greater than C, greater than E, less than I, so it must be this page. Somewhere on this page. And we will read down this page until we run out of G's. Because as soon as we go from G to something that is not G, we're done, because this is logically ordered. And we are going to navigate these pages, if we need to, by their next page pointers. And an index is always logically ordered by its keys. So the query processor can be completely assured that once it's read the rows for G, if it encounters H, there are no more G's anywhere in this index. Done. Happy with that? Right. Let's try an inequality seek. This is also a seek. We are also looking for a value. In this case, we're looking for the start of a range. We are looking for the value O, or we're looking for the first value that is greater than O. greater than A, greater than K, so this way. Not this one, on this page. Somewhere on this page, and since we're just looking greater than, we've got no upper bound, we just run and read until we run out of pages. There's no way, there's no limiting condition here. It's, okay, done, end of the index, that's all the rows. A seek, the definition of a seek operation is a navigation down the B tree looking for a row or the start or end of a range of rows. Happy with that? All right. Some more slightly more complex seek operations. Looking for less than or equal to L. Well, greater than K, so it must be this way. This page, because M's already too great, so we're not going to find our rows there. So here, and then we do a backward scan back down the table. This is not an index scan. This is an index seek, because we looked down the B tree to find the start or end of a range. This is often called a range scan. But if you're looking in an execution plan, this shows up as an index seek operation. And we've got a backward scan looking for the matching rows. SQL can seek backwards down index just as effectively as it can read forwards. The main difference is that for some reason, backward scans cannot run in parallel. They're in serial only. So if we had done a seek down this side and read up, which we can't for this predicate obviously, for this predicate, this could technically be done in parallel. Now, for a table this small, we'd never run this in parallel, but let's assume this is a couple million rows. This could be done as a parallel index seek. This cannot, because it's going backwards down the index. Don't ask why, it's just a limitation in the query processor at the moment. Maybe next version they'll take it away. I don't know. All right, so on to a two-column seek. SQL is perfectly capable of seeking when it's got a two-column index and a two-column predicate that matches that index. It will seek on both predicates at once. So we're looking for E, so obviously this way. Now we've got two possibilities. We've got two pages that have got E on them. But we're looking for greater than or equal to 10, so this page is completely irrelevant. It cannot have any values 10 or higher on it, because this one starts at 9. So this page is not touched. So we're going to go to this one, and we're going to read until we run out of E's, basically. The very common misconception I've seen is that SQL will seek on the leading column only and read both of these pages. No, it won't. It's perfectly capable of evaluating multiple predicates in a seek operation, providing the index supports them, which this one does. You guys happy with that? It'll become very important when we're doing index design a bit later. Okay, so the other one I wanted to mention is lookup. I don't have any diagrams for a lookup specifically. A lookup is to a clustered index only. You will never get a lookup done to a non-clustered index. It's not possible. A lookup is, by definition, a single row clustered index seek. And by the way, all of these, if you looked in the execution plan, if you looked in the index usage statistics, would show up as range scans. Because in every single case, these have been seeks on a not unique index. If I define this index as unique, and we'll pretend for the moment that this is E3, then a seek for, let's say C1 equals E and C2 equals 5 will be what's called a singleton seek, a single row seek. Down here, find that one, 5, and we're done because we can only have one of them. This index, since it's not unique, what SQL will have to do is find the first row that's 5 and read until it runs out of 5s. In this case, there's only one of them, but it still does have to check to see that the next row isn't also 5. So these show up as range scans. They are index seeks, but they're index seeks for a range of rows. You get a singleton seek when you've got a unique index and a seek on all the columns of that index. Sorry. A key lookup is a singleton seek because a clustered index is always unique. If you define it unique, it's obviously unique. If you don't define it unique, SQL adds an extra column to make it unique. So a clustered index is always, by definition, a unique index. And so a key lookup is always a singleton seek, seeking down the clustered index for one row. That's what makes them so expensive, by the way. Everyone happy with that? Seeing some frowns. Yes? It'll find. So if you've got an if exists, and max works the same way, and select top one, exists is looking for a row. As soon as it finds a row, the exists is satisfied, out. So if you did if exists select star from table with a billion rows, it'll read 1. Because it doesn't need to read any more than that. It'll probably still show up as a range scan, but still it hits 1 row. Actually, it would show up as a range scan, because technically it is. It's just a range scan that aborted after 1 row. Just like if we did select max, let's select top 2 from table, order by C1. That's an index scan, but it aborted after a single 2 rows were read off the first page. Okay. I'm going through this way too fast. Alright, so non-clustered index design. And let's assume that we have got a single predicate. Nobody even cleared my whiteboard off. Okay, I cheat. That's better. Quickest way to wipe a whiteboard. Alright, so let's say we've got that table, C1, which is a single character, and C2, which is an int. Yes, my handwriting's terrible. So if we've got a query, that's fairly easy. I do my clicker. Because we've seen that we're looking for C1, so we can seek down that one, and find it somewhere there. Happy with that? Simple enough. What happens if I've got, instead of C1, wiping it with my hand when I've got the eraser in my other hand. Can we evaluate that as a seek operation given that index? We can't, because 5 is, well, where is 5? All over the place. Because it's the second column, and so 5 will be in there. Well, we've got a 5 there. We might have some 5s here. We've probably got some 5s there. So this can only be done as a scan. So if we want an index that will support this query, then we need a single column index on C2. An index on column 1, column 2 cannot support a query that filters only on column 2. So when you're doing index design, when your queries have single predicates, that single predicate has to match the leftmost column of the index for that index to be saggable. used as a seek operation. If it matches the second column or onwards, you've got an index scan. That's the best you can get. It's nice and easy. And yeah, okay. So how about multiple equalities? This is okay. So let's say we've got two queries now. One index do those two want? Actually, can they use one index? That's the first question. Someone sounds quite certain at the back. They do the same thing. And yes, I'm playing nasty and trying to trick you this late in the day. Order of columns in a where clause doesn't make any difference most of the time. Shouldn't make any difference. Both of those can seek quite happily on an index on C1 and C2. So when you're looking at multiple predicates, when you're looking at queries with multiple predicates, you can, let me try that again. So yes, to seek effectively, these two need an index on column 1, column 2. How about that very common indexing strategy of an index on column 1 and an index on column 2? Does that work? I see people shaking their head. It actually does work. SQL can do it. What you get is an index intersection operation. So what you get is SQL will find all the rows which match the one predicate as one seek operation, all the rows that match a second predicate as another seek operation, and then intersect the two. It does work. It's also remarkably inefficient. So if you see systems that have done that lovely indexing strategy of a single column index on every single column in the table, I can tell you that 3/4 of those indexes are completely useless. Probably 90% of them are completely useless. Because the only thing that a single column index supports fully is a query on a single column. And I don't know about you, but I don't see too many queries that look like this. I don't know. Maybe you see that in your systems very often? But I can only select the same column. So, yeah, not very useful. Yes? Yes, you could. Let's ignore that for the moment. I'll get technically a non-clustered index is never a single column index, but well, I'll talk about clustered and non-clustered a bit later. We'll try to pure index design. We'll talk about clustered. Yes, technically I could pull the clustered index column in there as well. So if you've got queries that have got multiple predicates, to support them properly, you need indexes that have got multiple predicates. And when you've got this kind of thing, the order doesn't matter. So for the purpose of these two queries, it doesn't matter in the slightest whether the index that these two will use is C1 followed by C2 or C2 followed by C1. Both of these index queries can seek perfectly well on both of those indexes. Where it becomes important, where the order of the predicates, so where the order of columns and indexes become important, is when you're trying to support multiple queries with as few indexes as possible. Because I don't tend to see systems that only have a single query on a table. I know, maybe you do. But typically I see systems where there's multiple different queries against each table. So this table might be getting queried by surname and first name, ID number, telephone number and surname, that kind of thing. When you're trying to support multiple predicates with multiple queries with as few indexes as possible, that's when it becomes very important to get the index or column order correct. Because if these were the two index queries that I was trying to support on this table, well, now what's my index column order? C2, C1. C2 supports this one. Mine supports the first one. If I put C1 as the first column, only this one would be able to seek. The other ones would not. So there's a very annoying piece of advice that still keeps flitting around. Put the most selective column in the index first. Firstly, that one's very prone to misinterpretation. I saw one system once where every single non-clustered index started with the primary key column. And when asked why, the person replied, I was told that non-clustered indexes should have the most selective column first. Of course the primary key is the most selective, it's unique. It was also completely useless, because these indexes did absolutely nothing for the system. Dropped the whole lot and then performance improved. There is a slight element of truth in that, but it comes way, way, way down the list. The first thing you want to do is support as many queries as possible. Once you've done that, then if there is still an ambiguous column order, maybe consider putting the most selective one first. But that's, yeah. It's got to do with the statistics and the row estimations, but to be honest, it's not a huge consideration. Unfortunately, I believe it's in the TechNet documentation, so of course it must be right. Yes, Hugo's snorting in the front row. There are errors in the MSDN documentation. Some of them have been around for years. All right, so it's multiple equality predicates. You guys happy with that? Okay. Inequalities. This is fun. Think about, let's go back to this one. If I say that I want, since I have a whiteboard here, let me use it. Ooh, that's a nice color. Usually orange pens don't work, but this one at least is sensible. How well can that index support that query? It can do it. It can be used as a seek, but it's not a very efficient seek. Because greater than m, I'm reading down, I've got to read all 4 of these pages, and only once I've read all 4 of those pages can I apply the second predicate. It's not very efficient. To support that query, I want to flip the column orders around so that I can seek for C2 equals 4 and C1 greater than m, or at least equal to m, find the end of that, and just read the rows that I want. That, while it is a valid seek operation, it will show up as an index seek. It's not in a very efficient index seek. If you're looking in the execution plan, you would see that as a index seek on C1 with a secondary predicate being applied on C2. The ideal that what you really want is, where possible, as seek predicates, but all of the predicates in your query. Seek predicates are what we seek down the index tree to find. So if we go back to this one, this search for E and the start of the range those both are seek predicates because I'm seeking down the tree to the start of the range and reading. This one would have no residual predicates being applied to it. But if I tried that query on the same index, I would get down to M as a seek predicate, and then the filter for C2 equals 4 has to be applied as a secondary predicate. Cannot be applied as part of the seek. That make sense? You're looking very confused there. Yes.
I understand that, but if you have a page which is say N1, would it still need to go to the page before to see
Yes.
the other ones?
Because the fact that the page starts with N1 doesn't mean that the previous page hasn't ended with N1, unless it's unique. And there's nothing stopping that there being an N0. The fact that I'm only showing 1 to 9 doesn't mean I can't have a 0 or a -2. So yes, we've got to find the last row that we need to find the beginning of that range, so we need to find the last row that isn't it, and then carry on going. That's why I said if I was seeking here for E and C2 greater than or equal to 9, I would have to read this page. The fact that I start with 9 doesn't mean I haven't ended with 9. Yeah. Everyone else happy with the... I know I'm bouncing backwards and forwards. Everyone else happy with inequality predicates? Who's looked at the missing index DMV recently? You'll notice that you're given the columns as equality, inequality, and include. It's for exactly this reason. Because when you're creating an index, if you're going to create an index to support that missing index, it's equality columns first, inequality columns second, includes as includes. Now that's all well and good, but here's a real fun one. What's a good index for that? And no, you don't read my answer off the slide. Good question. I don't appear to have. Yeah. This one is going to depend on a couple of things, in fact. These are probably parameters, not constants embedded in a query. My developers are not usually that nice to me, to hard code values that they are always searching on. So it depends on two things, your knowledge of the data distribution and your knowledge of how that query is used. Because this could either be C1, C2 or C2, C1, I don't know. What you're looking for is the column order in the index that allows SQL to reduce the number of rows that it needs to look at as fast and as early as possible in the query. So whichever of these two will normally reduce the row count the most is the one I want to put first in the index. And of course I want to consider all the other queries on my table. Maybe I have a lot of things that do an equality search on C1. In that case I'm going to put C1 first because I want to support as many queries as I can with as few indexes. I don't like index bloat. As an aside, what's the largest number of indexes anyone's ever seen on a table? 30 something, okay? 30 something. Anyone beat 30 something? 57. I've seen 57 non-clustered indexes on the big, fastest inserted transactional table in a system. That was fun. Somebody had run DTA and taken all of its suggestions. It was pretty. No, it wasn't. It was as ugly as hell. So you don't want index bloat. You can't go and create the best index for every single query you've got. Maybe if you've got a data warehouse, you can get away with that. OLTP, definitely not. So what you're trying to do is support as many queries as you can with as few indexes as you can, so you often will end up with trade-offs. Maybe for the best index for this starts with C1, but I've got queries which filter equality on C2. I want to flip it around because that's what's going to work best. Compromises. The most important queries are the ones that run the most frequently. And of course the ones that the boss in the corner office runs. That's always important. But you're trying, in general, if the fastest queries in the system can use a certain set of indexes, and some slightly less important queries can use them less efficiently, that's fine. They're not that important, they're not running as frequently. It doesn't matter if they're slightly slower. In general. Doesn't always work that way. Anyway, that's equality predicates. What time do I have until? It's 10 past 6. Wow, over half an hour. Wonderful. I'm nearly done here. Okay, so all predicates. That's another fun one. And that text is completely wrong, because apparently I copied it from the other slide and didn't fix it. Whoops. Let's fix that. Right, that's better. Well, at least it's now correct, because it was blatantly incorrect before. If anyone has any aspiring presenters in the audience, it is sensible to actually do a proofread before you present. I had an old index deck that I used to use, and I'd been using this thing for ages. And one presentation at Past Summit, someone puts up her hand and says, "That index is wrong." I'm so, "What do you mean it's wrong?" And she says, "The third page from the right, the key orders are reversed." I'm sort of, damn it, you're right, they are. I'd been using that particular example for about 4 years. Nobody had seen it before. It had also ended up in a couple of Simple Talk articles. Nobody had picked up the fact that the index key orders were reversed. Whoops. Yes, you'll always have some attentive person in the audience. Anyway, it's better. C1 is a character, isn't it? It's 1. Okay. That's fun. Because the indexing rules for those two are completely the opposite. For the first one, with the AND predicate, I want one index, because SQL does not like seeking on 2 indexes and doing an intersection, because intersections are expensive operations. It's essentially, if there were separate indexes on C1 and C2, to satisfy the first one, which is an AND, what SQL would have to do with 2 indexes is seek on one, seek on the other, and then essentially join the 2 queries, the 2 index results together. That's expensive, it doesn't like doing that. So for the first one, you want one index on C1 and C2, or C2 and C1, doesn't actually matter. The second one, being an OR predicate, is exactly the opposite. Because where an AND reduces the number of rows in the query, every subsequent predicate decreases the number of rows that qualify, in theory. And OR does exactly the opposite. The more OR predicates you add together, the more rows you get. The bottom one, the OR predicate, cannot use a single index. Well, not effectively anyway. Because these are considered 2 separate predicates. So if we were to go back to this, I can use that for the first part, C1 equals A, that's dead simple. But this is not something that I can do secondary. I can't go and look for A4 because that's not what I want. This has got to be a separate seek operation. So where are my 4s? Well, this would end up with a scan. So where this one, with the AND, you want one index with all the columns in. With an OR, you want multiple indexes, each with one of the columns in. The correct and optimal index for this particular predicate is one index on C1 and another index on C2. because it cannot use a single index unless it scans the index. If you don't have one index on each one, what you'll get is a table scan or an index scan. If I had that index for this query, what I would get out would be quite simply a table, an index scan. Read along the index and throw away the rows that it doesn't need. Does that make sense? There's a bunch of problems with ORs. It can sometimes be easier to take the ORs and turn them into a union. Sometimes you can get better query results out of that, sometimes you don't. It is something worth checking though. I've had problems before where I create indexes for both of them, but SQL won't use them because it's getting the row estimations wrong. Sometimes multiple queries with an OR is more efficient, sometimes it isn't. It's going to be a toss-up. And I'm going to finish this session way early. All right, so that's ORs. I'll correct this before I hand it to Neil for posting online. All right, so predicates and joins. Before I carry on with that, is everyone happy with the stuff so far? Is there any questions you want to ask? Anything you're unsure of? Okay. I can tell you we're not going to be running over for the raffles, which is probably a good thing. Anyway, predicates and joins. I sometimes get forum threads asking, what indexes do I create to support this join? And quite often that's the wrong question. Because the majority of use of an index is to allow SQL to find the rows that it needs quickly. And in many cases, joins don't reduce row counts. In many cases, joins are just there to fetch the matching rows from two tables. They're not there to filter the results. They might, but they might not. If I'm joining from my customer table to the city table, that's not going to reduce row counts. That's just getting the city data. If I join from there to country, that's also not reducing the row counts. That's fetching the country. However, if I'm joining from customer to order and filtering the orders, it probably will reduce the customer's table. It's a trade-off, and it's something you have to consider. But the primary use for an index is to support where clause predicates. So if you've got a query that's got where clause predicates in the where clause, that's what you want to look at for indexing first. Joins is a secondary consideration. And it's not something you're going to create a second index for. If you've created an index on column 1 for the where clause, and the join is on column 5, creating a second index on column 5 on the same table is going to be absolutely useless. SQL won't use it. It's not going to go and fetch a second index to do a join operation. Way too expensive. The other thing is that your join types themselves do not always use indexes. So you've got 3 physical join types in SQL Server. The nested loop works by taking each row in the outer in the outer table, and doing a search on the inner table for that value. Hence, a nested loop can very happily use an index on the inner table on the join predicate. And if the inner table also had a where clause predicate, the combination makes a very useful index. The combination, the where and the join in a single index, not in 2. A merge join, on the other hand, doesn't do seeks on the join columns. The merge join, all it wants is that the 2 result sets are sorted in order of the join column. So whereas the nested loop, if I was filtering for the inner table, filtering on one column and joining on a second, I could use an index with either column order, it would be fine. With the merge, it won't. With the merge, I've got to have the predicate, the filter column first, because that might, and it's a might, allow SQL to use that index for a sorted result set. Remember, indexes are logically sorted in order of their keys. Let's go, sorry. So if I was filtering on column 1 and joining on column 2 and it was a merge join, we could filter and the rows that come out are ordered by the join column, which is perfect for the merge. For a nested loop, if I was filtering on column 2 and joining on column 1, the join to the inner table, it's a filter, and it would be a filter on where clause predicate and join predicate, and it wouldn't matter which order my columns are in. For a merge join, it matters very, very much. And a hash join couldn't care less. Because a hash join doesn't need an index in the first place, the hash join takes both result sets, hashes one to create a hash table, hashes the other to look into the hash table. Index on that column? Pretty irrelevant. The only thing it mightn't help with an index is for the row estimations, but accurate statistics will do that for you too. So what kind of join you get very much depends how you're going to index for that join. And bear in mind, these will change as your data volumes change. So this is kind of, I call this advanced indexing, because the majority of the time you're indexing, you're going to be indexing for your where clause predicates. That's what gets you the majority of the gain. Can I also support my join? That's most of the time a secondary consideration. It's worth looking at, because if you can get away with it, it can give you some good results. And sometimes you can get SQL to change a hash join into a nested loop by providing an index that is on the where clause predicates and then the join predicates, or reverse order. And then it will more happily use a different join type. Does that make sense? You'll often see advice on indexing foreign key columns. Create indexes on your foreign keys to support the queries. A lot of times that's not for the joins themselves. A lot of times that's for when you're doing updates or deletes that need to do a foreign key check. They need to go and check, is there a column, is there a matching row in the other table? That is when an index on the foreign key columns can be very useful, because those lookups can be quite expensive otherwise. If you're deleting 100 rows and SQL's got to go and check the foreign key and there's no supporting index, you could end up with a table scan of a massive table instead of a few index seek operations. Make sense? Right. One more thing. Yeah. And I apologize, I'm going to finish this one way early, so if you've got questions, please. Otherwise, it's going to be an early afternoon. I don't actually mind. All right, so indexing for aggregations. This is quite a fun one. This, again, is definitely, I'd call this advanced indexing, because you're not going to get away with it most of the time. It doesn't work most of the time anyway. If I've got I can use an index to support that predicate, to support that order by. Not predicate. To support that order by clause. Because the data that comes out from that sequence C1 is ordered by the second column in the index if there was one. Which means we've got an order by clause that SQL doesn't have to actually go and do any work to do. Now that doesn't mean you can leave off the order by clause. If you don't, you get rows data back in any order the optimizer and query processor feel like giving it back to you. But if you do have an order by clause like this, and you've got an index C1, C2, that's almost a free order by, because there's no sorting that needs to be done, because the data is already sorted in the index. Same thing applies. Group by. Group by is an interesting one. There's two ways that the optimizer can choose to do an aggregation. Stream aggregate, hash aggregate. Stream aggregate requires that the data coming in is sorted by the group by columns. But the optimizer is not going to go and choose to put a sort in so that it can get a stream aggregate. Sorts are expensive operations. If, however, there's an index which results in the data coming out already sorted, you can get a nice cheap stream aggregate instead of the rather more expensive generate a hash table, hash all my data into the hash table so that I can do my aggregation. Just bear in mind, this does not work as soon as you've got an inequality. Because as soon as you've got an inequality, the data coming out of that inequality predicate is no longer ordered by this. It's ordered by C1 because we've got multiple values of C1. Don't go creating indexes to support order bys at the expense of your where clause predicates in most cases. You will find edge cases. You will certainly find situations where it is cheaper to put, it's cheaper for the query to run as an index scan with some filter, with some secondary predicates, than to run as an index seek and sort the resulting data. The optimizer is often quite good at choosing that. Not always. It's worth testing sometimes, especially if you've got a large set of data coming out that must be sorted, has to have an order by clause put on it, and you can't support that with both. You can't get an index that supports both the predicates and the order by. It's sometimes worth testing. If I support if I support the order by, is it cheaper than supporting the where clause predicate? Typically, when you get that, it's a case where the query is returning a large proportion of the table, and I do mean in its point 70-80% of the table. So it's filtering out quite a small portion, and then sorting the whole damn thing. Because sorts are really, really expensive operations. You're looking very troubled there.
One of your questions, if you have a multi-column index,
Yep.
and you don't
Group by, unless you're doing grouping sets, the columns in the group by is a list. It's not grouping by one and then the other and then the other and then the other. It's grouping by these. I don't think it matters. Order by definitely matters. Group by, as I said, unless you're doing grouping sets, I don't think it matters. Okay. I have confirmation from the front row it doesn't matter. Hugo's useful. I remember saying something one presentation before, and they're going, no. I'm sort of, what? Turns out I had said something completely incorrect and no one realized it. So group bys, yes. The order in the group by doesn't matter unless you've got the grouping sets or roll up, cube, one of those advanced grouping operators. Anyone else? Okay. Right, multiple queries. I've spoken about this a few times already. When you're trying to support multiple queries with as few indexes as possible, this is when column ordering becomes very critical. And I can promise you there is not going to be a simple solution here. You're never going to end up with a situation where you can support all your queries perfectly with 3 or 4 indexes. Unless you're working in a really, really simple system. What you'll probably end up with is a situation where you can support the majority of your queries fairly well with 4 or 5 indexes, and the others, well, whatever. It becomes important here to make sure you've identified the most important queries for the system. The ones that run most frequently, the ones that are most time sensitive. If you're working in an environment where certain queries must execute in under 20 milliseconds, well, those are definitely going to be the ones you target for the best indexes they can possibly manage. The stuff that runs on a schedule every hour and emails itself to a bunch of people, you know, if it runs 2 seconds longer, I probably don't care, because I can always blame that on the email server. Sometimes it's handy. This admin's not exactly going to argue with me that the email server's slow. If there's anything like my network admin, it'll be the email server's slow. Oh, not again. No, but seriously, make sure you know what's important and what's not when you're doing index tuning, because you are never, ever in a million years going to satisfy everything perfectly. Systems do not come out that cleanly unless you're setting up demos. All right, before I talk about filtered indexes, I've been ignoring the clustered and non-clustered index differences. So, a few things here. Yes, you get my very bad handwriting on a whiteboard. So, a clustered index, I'm just going to draw a really small one. If it is defined unique, great. This would be create unique clustered index. If I have not defined it unique, SQL will make it unique. Clustered indexes are always unique. They have to be, because they're used as the row's address in other indexes. So if my index is not unique, this would be create clustered index. SQL Server will go and make it unique. It adds an invisible hidden integer column that is called the uniquifier. If I ever find out who named it that, I think they've got no tolerance for the English language. It is called a uniquifier. It is null on the first instance of that value. The first duplicate gets a value of 1, I think. I don't think it starts at 0. 2, 3, 4, 5, and so on. And it always increases. And the fun thing here is if I come later and I delete this row, and I delete this row, and then I put them back, the uniquifier always increases, which generates some really fun things. Integers have a maximum value of 2.1 billion. These are signed integers starting at 0. It is entirely possible, if you try hard enough, to overflow the uniquifier. You've got to try really hard, because you need either 2.1 billion duplicate values in a clustered index that's of the same value, or you need to have deleted and inserted a total of 2.1 billion rows with the same clustered index value. But it is entirely possible. And if you do this, you figure out that somebody on the SQL Server dev team had a sense of humor, because the error that's thrown is error 666. I'm serious. I don't know what the text of the error is, but yes, it throws error 666. Something about run out of uniquifiers. Somebody actually tried it. It's quite fun. We actually had a discussion about this. I think it was on the MVP mailing list. Somebody has actually seen this in a production system. Yes, they had deleted and inserted enough rows with the same clustered index value that they hit 2.1 billion on the uniquifier. I don't actually want to know what the hell they were doing with that system. But that's the clustered index. Everyone happy with this? Right. Yes? Yeah, you pretty much have to, if I might suggest, drop the clustered index and put it somewhere else. Because, yeah, not even going there. But yes, you pretty much have to drop and recreate the index. I don't think a rebuild fixes it. I can't imagine a rebuild resets. Doesn't, yeah, of course. Of course, it does not renumber the uniquifier. Yes. That's interesting. Okay. I suppose it would do. So, in other words, to generate that, you would have to have deleted and recreated 2.1 billion rows without ever having deleted all of them. Great. The thing people do with their tables. But yes, drop the clustered index and recreate it, and if that table really has 2.1 billion rows, do have a nice week. No, create it somewhere else. All right, so that's a clustered index. Let's have a look at a non-clustered index. And we will assume, for the purposes of creating this non-clustered index, that the cluster is on C1 and it's not unique, so we've got a uniqueifier, which we're just going to call U. So let's create a non-clustered index on column C2. And we will assume for the purposes of this that C2 is not unique. Okay. The non-clustered index has been defined on column C2, but because this is a non-clustered index, the clustered index key is added into the non-clustered index. And because this non-clustered index is not defined as unique, it's added all the way up the tree. So we've got the clustered index column itself, and we've got the uniqueifier, and they've been added at all levels, all the way up the index tree. They are essentially considered the same as if they were key columns in the non-clustered index. So this means that a non-clustered index on C2, when we have a clustered index on C1 not unique, is essentially the same as a unique non-clustered index on C2, C1, and the uniqueifier. And it is logically the same. It looks exactly the same. If I was looking internally, I would not be able to tell which of these it was, unless I'm looking at the metadata. Now, happy with this? Okay. Now, let's assume we have another non-clustered index. But this one actually is unique. And this one's on C, column 3. We'll conjure a column out of nowhere. Because I'm tired of making up values, I'm just going to assume it has a long complex value. Let's call this a grid because they're nice and handy. So this is a grid and it's unique. Whatever. This one, it's a non-clustered index. It still gets C1 and the uniqueifier at the leaf levels. But the only thing that appears in the non-leaf levels is the non-clustered index key, because it's unique. When a non-clustered index is unique, the clustered index key is treated as if it was an include column. When a non-clustered index is not unique, the clustered index key is considered part of the non-clustered index key and is present at all levels of the non-clustered index. Make sense? Okay. I will recommend that for index design, you don't depend on this. So for example, let's say that's our clustered index on C1, and you need, for a particular query, a non-clustered index on C2, C1, include C4, whatever. Create your non-clustered index C2, C1, include C4. Don't depend on the fact that C1 is the clustered index key and is included implicitly. Because that's all well and good until somebody moves the clustered index to C5. And suddenly your queries take a nosedive in performance because the index no longer supports them. You're not losing anything by explicitly placing that column there, because it would have been there anyway. It would have been there as part of the clustered index. By adding it explicitly, SQL doesn't add it a second time. It's not silly enough to duplicate columns in an index. If you need it there, you put it there. If we have if our clustered index is on C1 with a uniquifier, this is a non-clustered index. C2, C1 uniquifier includes C4. And this is a non-clustered index, essentially C2, C1 uniquifier includes C4. So you don't lose anything, you're not adding extra overhead by explicitly adding the column in, but you are giving yourself some future proofing so that if when sometime somebody moves the clustered index somewhere else, your indexes don't suddenly stop supporting your queries. I'm not a major fan of brittle code, and this is basically brittle index design. But don't you're not costing yourself anything. It's not a case that SQL will go and add the column into the index a second time. It's not that stupid. It'll only be there once. Happy-ish with non-clustered indexes and how they actually look under the cover. Cool. By the way, the difference between a unique constraint and a unique index is that a unique constraint's name is unique within the database rather than the table, and it can't have include columns. Other than that, there's no major difference. So there's no penalty for saying unique indexes instead of unique constraints if you need to make something unique. And making it a unique index means you can add include columns, which you can't do on a constraint. It's one reason I'm a lot more fond of unique constraints, of unique indexes these days than constraints. Yes, sir. Getting there. That's called excellent question. It's on the next slide. But you saw that earlier because... All right, filtered indexes. I mentioned at the beginning that there is one case and only one case where an index can have fewer rows in it than are in the table it's based on, and that's a filtered index. A filtered index contains, well, a filter predicate. Create index, blah, 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 on table, these columns, where, condition. It has to be a simple condition. It cannot have ors in it. There's a whole bunch of limitations on it. Nothing, basically it's column comparison value. That's it. No ors, nothing complicated. I don't know, can I even have and predicates?
You can have and, you cannot have or, you cannot have not.
Okay, so no nots.
But you can use an in list.
Okay, you can have an in list if you really want one. But it's a list, not a table. No nots, no ors. So it must be a very, very simple column equals value and column equals value. Greater than, less than, they do work. To be honest, I've never been all that fond of these things for query optimization because the query's predicate must match the index's predicate or be an easily identifiable subset. And that catches a lot of things out. So a classic place I see this being used is for soft deletes, where you've got an is deleted column. So if I create an index, okay, so if I create an index and I specify where is deleted equals 0, and we will assume that is deleted is a bit, enforced not null, so it can only ever possibly be 1 or 0. And I have a query that goes can that query use that index? Assuming, of course, that the index columns match the rest of this query. Who says yes? Theoretically, it should be able to, because these are identical predicates. Let me make that clearer. is deleted as a bit, not null. It can only ever be 1 or 0. So if it's not equal to 1, it's 0. Cannot use it. So the optimizer's not quite smart enough to figure out that these two are the same thing. The other place that this goes really badly is when my index I don't know. And we will assume it does all the date conversions correctly. And my query has forget about it. It's parameterized. There's no way to tell whether that index matches this. You won't get it in. You will not get the filtered index used. It's annoying. The only time I do like this is things like is deleted, is active, that kind of thing where it's 1 or 0, and then I make very, very sure that developers getting their predicates correct, which of course is a little hard these days with Entity Framework and the garbage that it puts into the database. You can get there sometimes. But where this is really useful is for complicated unique requirements. For example, let's say that a customer can only have one active order at a time, but he can have multiple inactive orders. How would you enforce that with a unique index? Well, here's an interesting... Actually, let's not do that one. You can have multiple rows where completed is null, but only one row where completed has a value. Here's a fun thing. As a constraint, a unique constraint, considers null equal to null, you can have exactly one of them. Yeah, don't go there. Nulls are not equal to nulls unless you're dealing with unique indexes or about 6 other places. So you can't do that with a unique constraint of any form. So what you do is a unique index filtered where this column is not null. Create unique non-clustered index, this column where condition. Very, very handy, and that is one of the really powerful uses of filtered indexes. Unfortunately, they don't tend to be all that useful for actual queries because they are so prone to not being used. As soon as you've got parameterization, they will not be used. End of story. And you've got to make sure that the predicates match exactly or is identifiable subset. Pretty much a pain in the neck, to be honest.
Would you get kind of object behavior if you had a merge statement, which was flipping the old
Merge and filtered indexes is just asking for problems. That combination's got how many connect items filed on it? Merge actually breaks filtered indexes and vice versa. So as soon as you put the two together, I'm not even going there.
The usage of filtered indexes for performance, I have found that if you have an included column for the filter column, even if it appears redundant, it does sometimes...
Yes. Thank you. And there's another bug in filtered indexes, which has been closed won't fix since 2008 on Connect. Thank you very much. If you've got a filtered index for column is not null, you've got to put that column into the key or include, or the index will never be used. Just plain never be used. So it gets a little fun sometimes. Very nice for unique requirements. Very finicky for actual usage. Tread carefully. If you can get them working, great. If you can't, go back to a normal index. All right, and that is pretty much everything I have to say on indexes today. Kimberly is probably the authority on indexes, so go read her blog posts. She occasionally posts something new. And that's my list of rants and raves on indexes. You'll find some fun stuff there, I hope. And that, any other questions? Yes, sir. Will it work with option recompile? The answer is maybe, depending on things that we have not yet determined. Set options most likely is what's screwing that up. Finicky as hell. Yeah. So yeah, it might. It's something that needs poking at. I would expect it to work, but I won't be overly surprised if it doesn't. Is that these things are annoyingly finicky. Any other questions? Yeah.
See some blog posts suggesting that if you have heaps and non-constant indexes,
If insert performance is the most important thing for you, please go and make sure you've got Enterprise Edition and create a in-memory table. You're never going to get performance out of a row-based table that you'll get out of Hackathon for insert performance. That's what the damn thing's designed for. As for heaps and non-clustered indexes, maybe. Heaps have got some nice little side effects, including the inability to actually deallocate pages in deletes. Yes, heaps. Heaps, table without a clustered index, just make sure everyone knows that. They don't deallocate pages on deletes unless the delete was done with a tab lock. I have before now seen an empty table that took up 700 megs of disk space. I'm serious. Select count star from table, returned 0. But it allocated 700 megs worth of pages, because none of the deletes had been done with tab lock, and so it couldn't deallocate the pages. So I had hundreds, thousands of pages that were completely empty. It took forever and a week to do a count star. 0 rows. Absolutely fun. Try it. Honestly, try it.
would subsequent deletes with tab locks clear all those pages?
Yeah, maybe. The fastest way to clean it is just to truncate the table. Or put a clustered index on it. Truncate will do the job. Clustered indexes fixes it permanently. Nothing's perfect, but I'd say that one's one of those, go test it, because it's going to very much depend on your scenarios. But don't consider Hackathon for high insert performance, because... Anything else? Any other questions? Okay,
The view for missing indexes is generally run
okay, so a side note, where the missing index DMV's data comes from. The optimizer, as it's part of its job of optimizing a query, looks at the query and says, could I have done a better job on this query if there had been a particular index? It's considering just that index and that query. It's not considering what else runs on the server. It's not considering the query it optimized 10 milliseconds ago. It's not considering what other indexes exist on the table. It's purely the optimizer going, could I have done a better job with a particular index? They are a good starting point. They are not your ending point. Start there. See whether the optimizer is completely nuts. Sometimes it is. It's very fond of requesting the entire table as the include columns. It's also very prone to recommending indexes which almost exist, just missing a column. It will never consider a clustered index. It will never consider a unique index. It will never consider a filtered index. It will never tell you to alter it to widen an existing index. Use them as a starting point for your index analysis. Do not, please, please do not put a job on your server that goes to the missing index DMV every night and creates every bloody index. Yes, I've seen blog posts recommending that.
Please do this. I will send you my consultancy rates.
Hey, I'm cheaper. Hey, I live in Africa. Of course I'm cheaper. That's a nasty argument. Any other questions before Hugo and I go and fight this out? In that case, thank you very much. Enjoy the rest of the afternoon.